Hello everyone, and welcome to the video presentation of our paper, Informed Deep Learning for Anomaly Detection in Cyber-Physical Systems. Our society is dependent on a vast network of interconnected cyber-physical systems. Transportation, energy, water, communication. Cyber-physical systems provide us with critical services that we require on a daily basis. As the complexity of this system grows, it becomes more difficult for humans to identify anomalies. This highlights the need for advanced anomaly detection methods. This is where deep learning can prove to be useful. So why deep learning? Deep learning models have the ability to learn complex decision boundaries for detecting anomalies. They can analyze vast amounts of data from multiple sources such as sensor logs and network traffic. Downside is that require a large amount of high-quality data for training, and DNNs are still used as black boxes. They provide a little to no information about the reasoning behind its prediction. One solution could be use of prior knowledge for fulfilling these gaps, so-called informed learning. What are the benefits of informed learning? We can fill the gap of missing data. We can improve trust in our model by adding well-known physical laws and equations, which may help to generalize better by constraining the function space. The main drawbacks of the informed learning: it will be an expensive, time-cost trial and error process. It's difficult finding the balance for the constraints so the model doesn't underfit or overfit the data. The main sources of prior knowledge are mathematical equations. They can be expressed as equalities or inequalities. We can use differential equations for capturing the dynamics of the system. We can discover knowledge from the simulation. We can introduce information about the relationships between the components of the cyber-physical system as knowledge graphs. Prior information may guide the selection of appropriate network structure that captures the best the features of the data. We can assign meanings to specific neurons or layers, so we can interpret the output of the deep learning models. Loss function is the main guidance of the optimization process, responsible for finding the parameters of the model. We can add additional constraints in order to help the model to converge to a solution that is more likely to be relevant and accurate. Prior knowledge can be used to create test beds or simulation to produce diverse and extensive data sets for training. There are various interesting techniques in the literature for informed deep learning. For informed data, we can highlight pre-training of the network with simulation data and graph-based pre-processing of the dataset for improved interpretability. Here are some examples of informed architecture that leverage prior knowledge about the domain that are applied. And for informed loss functions, the most popular approach is physics-informed neural networks. In this case, the loss function contains an additional term that forces the output of the network to satisfy the physical differential equations of interest. In the end, we would like to thank the Industrial Electronics Society for this opportunity and for